through relativistic quantum information, which is based on these two recent papers with Stillman, Ming, and Rowe. So this is today's outline. First, I will guide you to the motivation of our project and a very brief introduction to relativistic quantum information. And then I will talk about the main methodologies we use, including the model of the unrolled detector and also the detector field interaction in RQI. And also, we will talk about our recent progress, magic harvesting in both anti-de-Sitter spacetime and the CFTs. And finally, I will make a conclusion. So let's move on to the first part, motivation. So as we know, holography is a very important principle in modern physics, and it can be traced back to 1993 and 1994 by 't Hooft and Susskind, who asked the question, what if our whole universe is a hologram? And the main idea of the holographic principle can be understood as follows. So all the degrees of freedoms in the bulk or all the ingredients in the bulk can be encoded in a lower dimensional boundaries. So you can imagine a can of tomato soup. You can just read the labels on the boundary of the can to get all the ingredients or all the information of what's inside the bulk. So this is the main idea of the holographic principle. And one of the most remarking example is the anti-de-Sitter safety, anti-de-Sitter conformal field theory correspondence proposed by Madasela in 1997. And this is a very brief introduction to holography. And there are some challenges or open questions. So you may ask, is there direct experimental access or operational interpretation of the holographic principle? And this is the whole motivation of our project. And we want to ask, how can we probe the nature of spacetime in an operational manner that complements the holographic picture? So the short answer is RQI helps. So what is RQI? So RQI is short for the relativistic quantum information. This is a very new subfield that studies the quantum information tasks or quantum information protocols in relativistic settings. By saying relativistic settings, I mean when the spacetime is curved or when the observers are non-inertial. And the RQI didn't just appear out of nowhere. It stands on the shoulders of giants. It incorporates ingredients from general relativity and also the quantum field theory in curved spacetime, and for sure the quantum information theory. And there are lots of interesting phenomena in RQI, including the unroll effect, which I will discuss in the next slides, and the entanglement harvesting. So entanglement harvesting is just that you consider two unentangled detectors, and then the detectors locally interact with the quantum field. And finally, you will find that the initially unentangled detectors become entangled finally. So that is why we say we can pull something out of nothing. We really harvest the entanglement from the vacuum state of the quantum fields. And all of these kind of interesting phenomena will involve the key concept called the particle detectors. So what is the particle detectors? So now let's move on to the next part. So you may ask this question first, what is a particle? So you may answer, oh, it is excitation of the quantum field. Yes, but the key point here is that the particle concept is really observer dependent. So for example, if you are in flat Minkowski spacetime, and if you are an inertial observer, and you will say, oh, there is no particles. I just say vacuum. It's just the vacuum state of the Minkowski spacetime. But if you are Rob, so by saying Rob here, I mean Rindner. So if you are a Rindner observer, which means that you are uniformly accelerating, so you will say, hey, I see thermal particles. So what do I mean by saying I see thermal particles? So I mean if you hold a detector, which is what we call an unrolled detector, you will detect particles. So the unrolled detector is just a very simple quantum mechanical system. For example, a qubit can be an unrolled detector. And when there is some field excitations, so for example, a photon, then your detector can observe the field quanta. You can observe a photon and let your detector go from ground state to excited state. So this will let your detector click. So when the detector click, you say, I detect particles. So this is a brief introduction of the Unruh effect and the Unruh-Dewey detector. And the key takeaway in this slide is that there is no unique notion of particles in curved spacetime, even in Minkowski spacetime when you are non-inertial. And the different observers will have different definition of the particles. And the particle is really whatever a particle detector detects. So this is our starting point. And in the following slides, I will consider a Q-thread Unruh-Dewey detector. And the reason why I'm interested in Q-thread Unruh-Dewey detector will be explained later. So this Q-thread Unruh-Dewey detector is just a 3-level quantum mechanical system, and it can be described by this free Hamiltonian. So you have your kit 0, kit 1, kit 2 with energy eigenvalue 0, omega 1, and omega 1 plus omega 2. And the state transitions between those states, kit 0, 1, 2, can be characterized by this monopole operator. So this part describes the state transition between kit 0 and kit 1. And this part describes the state transition between kit 1 and kit 2. And they are all determined by the energy gap here, omega 1 and omega 2. And how can we model the detector field interaction? So we use this interaction Hamiltonian, which is given by this expression. Here, lambda here is a coupling strength, means how strong your interaction is. And the chi of tau is a switching function, which means when you turn your interaction on and when you turn your interaction off, usually we will consider a smooth switching function. For example, a Gaussian switching function given by here. Here, tau is the proper time of the detector, and the sigma squared is like the variance. So we consider a smooth switching function. And here, mu of tau here is a monopole operator, describes the internal structure or the state transitions of the Unruh-Dewey detector. And the phi here is a quantum field evaluated along the trajectories of the detector's word line x of tau. So you will have local interactions along your word line, and this phi is just the quantum field operator evaluated along this trajectory. So this is the interaction Hamiltonian we will use to model the detector field interaction. And usually for a simple starting point, you will consider a detector in ground state, which is denoted by kit 0d. And you consider the vacuum state of your quantum field, denoted by kit 0. And you use the evolution operator, which is just determined by the interaction Hamiltonian we introduced before. So use this evolution operator, you can get the final state of your detector. So the final state of the whole system is just this evolution operator act on the initial state. And when you want to get the detector's final state, you need to trace out the degrees of freedom of the quantum field. So after this process, you will get the final state of your detector. And the detector's final state is given by this density matrix. It's a 3 by 3 matrix, where the 1 minus Q here, where Q here is the excitation probability to the first excited state. And the 1 minus Q here is just the probability of remaining in the ground state. And the beta here means the coherence between 0 and 2. So these are the density matrix of the detector's final states after tracing out the degrees of freedom of the quantum field. And using perturbation series, this step involves some calculations and involving the Dyson series. So after this perturbation series calculation, you will find that the excitation probability Q is given by this formula to second order to the coupling strength squared. And also the coherence, the off-diagonal term beta is given by this expression. And also here is lambda squared. And here chi is the switching function, and the W here is the Whiteman function. So Whiteman function is just the 2-point correlation function in that curved spacetime. And it is also determined by the energy gap, omega here. So this is the expression for the excitation probability and also the coherence of the final state of the detector. So now let's talk about our recent progress, magic harvesting in ancestor spacetime and CFT. So what is magic? So it is a lot like the magician plays a magic trick, pull a rabbit out of a hat. It is really something very physical. It's related to the modern quantum technology, especially the quantum computers. So in quantum circuits, there are some kind of circuits called Clifford circuits, and those circuits can be simulated on a classical computer in a polynomial time. So that's why we say the Clifford circuits are efficiently classically simulable. And there are some other kind of quantum circuits that cannot be simulated on the classical computer in a polynomial time. So we say these Clifford circuits can be described by the stabilizer formula. So they can be classically simulable in a polynomial time. So what is magic? Magic is actually the non-stabilizer resource that lets you go to beyond the Clifford world. So magic provides the missing resource that can let you go beyond this classical simulable region. So it can let you enable the universal quantum computation. So if you have these magic states or magic resource, you can have universal quantum computation, and this is the truly resource that signifies the quantum advantage and enables you to have the quantum computational advantage. And for magic, there are lots of measures. And in the following, we will consider mana, which is a well-established measure to quantify magic. And in the interaction picture, the mana is just determined by the final state of the detector. So it's determined by the Q, the excitation probability, and the coherence beta. And the reason why we are interested in Q trait is because that for the measure mana, it can only be defined in all the dimensions. So the Q trait is actually the simplest case that we can consider if we want to have a well-defined notion of mana. And recently, the group Nistra, Pazani, and Kiski, they show that you can harvest a magic resource from the vacuum state of quantum field in Minkowski spacetime. And they start with an initial state that has no magic. So it is the ground state of the detector. And after the detector field interaction determined by this Hamiltonian, and then they find that for the final state, the detector becomes a magical state. So it has non-zero magic. So, and in this protocol, they show that you can really harvest the magical resource from the vacuum of a quantum field. And there are also some related works. So including the harvest of stabilizer Renyi entropy in Minkowski spacetime, and also the harvesting of contextuality in Minkowski spacetime. And also more recently, people are interested in bridge RQI and holography. So they have related work like entanglement harvesting in CFTs. And also people are considering the magic of the conformal field series. So they show that the conformal field series are really magical. And also, people show that the gravitational back reaction is magical. And also, in consider the ADS-CFT, people show that the state update can be happen in both the bulk and the boundary. So those are all the related works that either trying to consider magical resource in more broadened concept or trying to bridge RQI and holography. So this is actually also our motivation. So we really want to let the RQI community and the holographic community communicate more. So we are doing this project starting from last year. So we show that the magic harvesting can be done in curved spacetime, especially the anti-de Sitter spacetime, because we are interested in holography. And we also show this year, we show that we can also harvest the magic resource from CFTs. And this is our setup. So we consider a static detector in anti-de Sitter spacetime of arbitrary dimension. This is the global coordinates of the anti-de Sitter spacetime, where L is the ADS radius, and the curvature is given by this. And we consider a static detector. The trajectory is given by this formula, where gamma here is just the square root of L squared plus R squared, and it is determined by the ADS radius and also the location of the detector. And in order to compute the mana, we need to compute the detector final states. That's why we need the Whiteman function. So the Whiteman function of the ADS spacetime is given by this. And it is determined by the gamma, which is determined by the ADS radius and also the location of the detector. And it is also related to the time difference of the proper time. Here, D is the spatial dimension, and the gamma is the gamma function. And the epsilon is just the regulator that is responsible for the epsilon regularization in the Whiteman function.
Now that you are in anti-de Sitter instead of flat space, you have a boundary. So what are the boundary conditions that you impose in your fields to get that?
Yeah, for this Whiteman function, we consider the transparent boundary condition, but you can also consider like Dirichlet or Newman. You just need to add some other terms. So this is the transparent. So you can add more terms to alter your boundary conditions. Yeah, thank you for your question.
And different, like in ADS-CFT, the choice of boundary conditions is very important to know what's happening in the CFT. Is that something important in your work or not?
Yeah, I will talk about later.
Okay.
Yeah, thank you for the question. And by some non-calculations that I didn't show in the slides, we obtain the analytic results for the transition and coherence for the Q-trait detector in anti-de Sitter spacetime. So in previous studies, people usually use the numerical integration to compute the final state of the detector, because usually in curved spacetime, Whiteman function is very, very difficult, and it's hard to get some analytical results. But finally, we obtain the analytical results of the diagonal term Q, and also the off-diagonal term beta here. And you may notice that they are very similar, right? So the only difference is just the exponent. They are different. This is omega plus omega n squared. This is omega squared plus omega n squared. And also here, this is 2 alpha, this is alpha, where alpha is determined by gamma here, and which encodes the information about the ADS curvature and also the location of the detector. And also omega n here, also it is like effective energy gap. So it is also related to the dimension of the anti-de Sitter spacetime and also the detector location and the ADS curvature. So this is the structure of the Q and beta. And if you do the calculation of mana, you may find that for the anti-de Sitter spacetime, it is really only determined by the linear combination Q plus 2 beta because of their similar structures. So this is the result, and you can use this result to get mana. And also, another interesting thing is that you can show that if you take the ADS radius very large, you can show that they can get the analytical results for the coherence and the excitation probability for the Minkowski spacetime. So you get these two formulas, and you just take D to 3 here. You will recover the results in their paper for the Minkowski 4. So these are some cross-check. And using other formulas, you can you can plot the mana versus the energy gap. So you may say that there is a first increase and then decrease, and there is a maximal value of the energy gap, meaning that there is an optimum value of energy gap that you can harvest your magic most efficiently. And also, if you enlarge your ADS radius, you will have larger magic, and it will approach the Minkowski limit, the black line. Also, we find the dependence of the magic harvesting on the dimensionality. So first, it also exhibits a similar structure, first increase and then decrease. But you will find that if you change your dimension, like if you increase your dimension, the magic harvesting will suppress. So this means that the magic harvesting is really favorable is preferred for the lower dimensional, for lower dimensions. And also, we want to study holography. So we consider a holographic setup. So we consider the conformal field theory in a Lorentzian cylinder, which is given by this line element. And it can be related to the line element of the ADS by performing a while rescaling. And in the holographic dictionary, the bulk operator phi in the bulk ADS is dual to the CFT primary operator O on the boundary. So we use this to study the magic harvesting in CFT. And the scaling dimension can also be related to the effective mass in the ADS bulk. So the effective mass is just the mass of the field plus the coupling. So you get the m squared L squared equal to delta minus d, where delta is the scaling dimension. And if you consider the simplest case, you consider a conformally massless scalar field. So you can have the two solutions of this equation. So we have two admissible scaling dimensions, delta plus and delta minus. And also, following the similar methods, you can get the analytical results for the CFTs, the Q and also the beta. And then you can get the results for the magic harvesting in the CFT side. You will see that it also exhibits a similar structure, first increase and then decrease. And there is a maximal or optimal value for the energy gap. And also, you can find that for larger scaling dimension, you will have larger magic. But for smaller scaling dimension, you will have smaller magic. And this means that the magic harvesting can be used to distinguish different scaling dimensions. And in the bulk view, can be used to distinguish different boundary conditions, because the scaling dimension is just related to different bulk quantizations, either the standard quantization or the alternative quantization. So this is the main result for the magic harvesting in CFT. And in summary, magic is a rabbit we pull out of the hat called vacuum. And in my research, I'm just trying to see if the hat has any hidden values for us to harvest. And hopefully we can get some insight for both holography and RQI. And there are a lot of references. And also we are grateful to those people, especially Professor Myers and Anru and Balasu Berminian and Prizini and Chen for insightful comments. That's all. Thank you.
Questions? I believe you mentioned that mana was only well defined in odd dimensions. Is this true? Do we know why this is? Or is should we expect that there's a notion of mana in even dimensions? And does this place restrictions on the types of space-time being considered?
Yeah, so especially when we consider the measure called mana, we need odd dimension because in its definition, it involves the discrete regular function, and that discrete regular function can only be defined for the odd dimensionals. And for example, if you want to let the dimension equal to 2 in that definition, you will encounter some problems, like you cannot define the inverse of 2 when you model 2. So that's the problems we will encounter when you want to define that for a qubit. So the simplest case is Q-trait. Yeah, thanks.
But it's not the dimension of space-time.
the dimension of the
detector.
Any other questions?
Why did you choose global coordinates in the ideas?
Because it's simple. Yeah, this is and you can write the global coordinates in ADS with a while rescaling to the safety on a Lorentz cylinder. That is maybe also another reason.
I always thought Poincare coordinates were simpler.
They are all simpler. And maybe another reason is the Whiteman function is easier to get in other coordinates because you can just consider embedded in a higher dimensional, in 5-dimensional space, and then you can easily compute the geodesic squared in that context. It's easier to get the Whiteman function.
So can you explain for delta plus and for delta minus which boundary conditions you use for each of them? Like boundary conditions on the boundary of ADS.
Yes.
Like you use different boundary conditions.
Yes. So here delta plus correspond to the standard quantization, which means you assign the slow fall off for the source and the fast fall off for the expectation value or the response. So, and this one corresponds to the other scenario, like you assign the slow fall off to the response. So they are different, and this fall off is actually related to when you expand your field operator near the boundary, they will have several terms. Which one is fast fall off? Which one is slow fall off? So this is correspond to different boundary conditions of the bulk fields. So that's why you can get 2 scaling dimensions.
So it is that the yellow one is going to be Dirichlet boundary conditions in the interior.
Yes, this is Dirichlet, and the other one is Newman.
Transparent boundary conditions before. I was confused about when are you using the transparent boundary conditions?
In the ADS.
But aren't these the ADS boundary conditions? The ones that you are saying?
Sorry?
Like this is, you need to impose boundary conditions in the interior of ADS and in the boundary of ADS. True? Like regularity conditions?
Mm-hmm.
Which boundary conditions will you impose in each of them?
So for this one is Dirichlet, and for the other one is Newman. Yes.
Okay, so no transparent boundary.
Yes.
Okay, thank you.
You might have talked about this in the talk, but can I ask why should I be surprised that you can do magic harvesting from the ADSFT? Because naively the coupling between the detector and the field will always be non-cleaver. So if you act on for example, trivial states, of course you will be able to get some magic. So what's the surprising part from this calculation?
Yeah, that's a really good question. So for us, the reason why we think it's important because magic is always very expensive, and we want to get the magic resource from some other scenarios like safeties, and we can use the magic harvesting from those field series to help us build some quantum computers. So this is the motivation for us to want to harvest the quantum resource from the field series.
The issue is that magic is only expensive in the setting of quantum computer because you want to consider Clifford gate in that setting, and Clifford gate is cheap there. But here you're considering some continuous time evolution between the detector and other stuff. In this case, if I understand correctly, the coupling is not Clifford, right? So naively, of course, if it's magic. You can also consider like a coupling between a detector with any other condensed matter systems will also be some magic, right?
Yeah, I think that's the point. That's the reason why you can harvest magic because the time evolution lets you to get that magic resource. I think that's right.
Okay, thanks.
Thank you.
Any final question? Let's speaker again.